on the main screen. There we go. And I think that's visible enough for our purposes. So my name is Scott Pierce. I'm a developer on the Vapor team up here at NCAR, along with my colleagues Sam Lee, Stas Jarosinski, and Nihat Chakuru. We are a team of 4, 2 software engineers, 2 project scientists, and we developed this thing called Vapor. It's a 3D visualization application. A question that we get a lot is, in the world of scientific visualization, there's a lot of options to pick from, whether it's ParaView, Visit, Maya, Blender, the list goes on. So what room does that leave for Vapor? And the answer that we have to that is that Vapor is tailored for the geophysical sciences. In my opinion, scientists don't typically even have enough time to conduct their science in the first place, no less go into the world of 3D viz. 3D viz comes with some inherent challenges, mostly because your data is occluded. By showing this third dimension, you're required to filter out more of it. And so it's much more complicated than just showing a 2-dimensional slice. So Vapor is open source. Our GitHub website is down here at the bottom right. You can go there to file bug reports, ask questions, and download the software. And we support 5 different operating systems right now that include Mac OS on ARM64 and x86 architecture, Ubuntu 20 and 22, and OpenSUSE. We're following the lead of our supercomputer with that one on OpenSUSE. We also support Windows, and we have a SPAC formula, if you're familiar with that. So you can compile Vapor on any platform you like using SPAC instantiation. We're currently working on a universal Linux installer, because no matter how many Linux platforms we chase, there's always seems to be one more user that wants something else. So universal installers are on deck, but not quite available yet. If you have questions, our website is over here, GitHub at the bottom, www.vapor.ucar.edu at the bottom right. And then those are our email addresses that you can contact us. Next slide. So the use case, like I said earlier, geophysical visualization is what we specialize in. All of our requirements are implemented because of user requests. And what that does, I think, in my opinion, is it makes Vapor easier to use than a lot of the other applications that are out there, because we don't have feature creep. The only features that we have are the ones that are specifically asked for us to implement by geophysical researchers. That streamlines our user interface, so you're not bombarded with too many parameters at the same time. In this tutorial, I'm going to go over 2 components of Vapor. Number 1 is the GUI, the desktop application. And then we have a new Python API that allows you to programmatically control everything in Vapor that we offer through the GUI. So in my opinion, in my use with Vapor, these 2 things go hand in hand and can't be separated. The way I use Vapor is I always start with the desktop application. I configure my renderers, my colors, and my opacities the way I like what we have in this background scene. And then I save a session file, which is the state of Vapor. From there, I can load that session into Python and then do things that are impossible to do with a mouse and a human clicking around and typing in numbers. By doing things programmatically, you can do things like what we call keyframing, flying through the scene in a cinematic way, doing orbits and scans like in an MRI. So I'll be getting to that kind of stuff in a few minutes. But some of the key concepts we'll be going over. I just want to, well, let's see, I have a couple more slides. The GUI is what we see right here. And just to speak to this real quick, up on the top left, we have this thing we call the renderer table, which lists all the renderers that we've instantiated. Vapor comes with 11 different renderers, and this is a list of the ones that you created. And to control them, you click on the individual renderer. So right here, the volume renderer is selected, and below that, all the parameters that pertain to that volume renderer are listed. On the right, of course, is the rendering of what you configured. And in the Python API, I'll be going through some Jupyter notebooks based on sessions that I've saved using Vapor's desktop. And then I'll be doing things that, like I said, are impossible to do with a human mouse. So key concepts, the renderers. Vapor comes with 11 different renderers. I'll be going through these. I'll talk more about them once I get the application open, but this is the renderer menu where you get to pick which one you want to instantiate and then parameterize based on what your observables are, what you're trying to get at. The session is what I mentioned earlier. It's like a save state file that allows you to save everything in Vapor, including the renderers you created, camera settings, the information from different data sets you loaded, and then other miscellaneous details. We'll be working with the camera and the Python API to do flybys, what we call keyframing. So we'll pick 2 different perspectives and we'll interpolate between those 2 to give a cinematic effect. And then finally, we'll be doing an animation, kind of like an orbit around the z-axis while animating through time, like what we see here with this hurricane. So one last note, I'm going to leave this slide out when I'm done, but we're looking for UX feedback. If you guys have any opinions on things that could improve in Vapor, if you could take a snapshot of this QR code, it'll take you to a Google form. And after each release, we will ping a few people just to get thoughts and opinions on things we're doing right, things we're doing wrong, and that kind of thing. Oh, let me leave that up for a second. All righty, I'll put that up again at the end if anyone's interested. But in the meantime, here I'll put out of my previous session of Vapor I was practicing on. So after I've installed Vapor, I guess there's instructions on that on our GitHub page. You just download an installer, and on Mac OS, you install like much other software. You just drag the icon into your applications directory and put it in the taskbar. And then you just open the application like so. And interesting. So on my screen, I have. I think that's good enough. So here's the basic user interface. It's all blank because we haven't loaded any data. There's nothing we can do right now. Up here we have a blank renderer table. Nothing's been instantiated. There's no data to read. There's no parameters down here in the bottom left because the same reason. And there's no rendering, etc. So the first thing we have to do is get data into Vapor. And this is one of the ways that Vapor supports the geophysical science community. It's the data formats that we natively support, because data ingestion is a huge pain for a lot of different applications. The data formats we cater to are WRF ARW, CF compliant NetCDF, which is generic NetCDF data that has a few attributes applied to the coordinate variables, so that Vapor can understand the grid that it's reading. And we explain all of this on our documentation page. If you go to vapor.ucar.edu and go to our documentation, go to Vapor GUI documentation. The data format requirements are here under data formatting instructions. And if you have NetCDF data that's generic, you can find everything you need to here, as well as all of the other documentation and video tutorials that you might want to watch from our docs. So back to Vapor. The data formats we support, WRF ARW, NetCDF, CF. We do support impasse. We can render three-dimensional impasse data. It's, I don't know what the right word is, but it's using an Intel-based renderer that, in my opinion, has trouble with contrast, but it does do an effective job at 3D rendering of impasse data. So I think it's not, if not the only tool for doing 3D impasse rendering, it's a sufficient one. But moving on, we also support a data format called brick of values. If you just have raw floating point or integer data on a regular grid, you can write a metadata file that describes your brick. And then Vapor will be able to read your raw data based upon the metadata that you write. We also support this data format we call data collection particles. So if you have Lagrangian data alongside your Eulerian simulation, we can render particle glyphs alongside the gridded renderings. And finally, we support UGrid, another unstructured grid format. For this tutorial, and again, all this data is available on the Google Drive, I think. So if let's see, put that there. Yeah, under tutorial 6, the data directory, there is this workout data from the East Troublesome wildfire that happened in 2020 in October. And so that's all there if you'd like to follow along or play with this at another point in time. I'm going to go to the import menu and select WRF ARW. And then, let's see, is this got too many objects? Let's see. I think this one right here. And I'll select all my files to load them all as a single data set in time series. So now click open. So now we have our basic setup. We've loaded our data. We have our data domain over here on the right. And you always kind of want to use a mouse with Vapor. Using the trackpad is doable, but the mouse is truly more finesse way of manipulating the scene. So the right mouse button can zoom out and in. And by the way, these same controls apply with the Python API. So if you're running the Jupyter notebook to manipulate the rendering in the notebook, it's the same thing. So right click to zoom out and in, left click to rotate, and then middle mouse button will reverse. Up here in my renderer table, at the top level of my tree, I have my data set. So if I click on that, I get some metadata information about the name of the data set, the location of it. I have metadata about some of the variables if I'm inclined to explore that kind of thing. And I also have this thing called a transform table. So 3D visualization and 3D simulations overwhelmingly in the atmospheric domain are huge on X and Y axes and very thin on the Z. Vapor will try to give a rough estimate on an appropriate scale factor on the Z-axis because if it's too thin, there's not much of a point in 3D visualization. So you always want to stretch it out. I'm going to go to my transform table for my entire data set and give it a stretch factor of 5. You can see my Z-axis. That was a stretch factor of 5 on my Z-axis, kind of got bumped up. The next thing I'll do is instantiate my renderers. So I'm going to click on this plus button up here in my renderer table. And we have this list of all the available renderers. Vapor supports WinBar based on 3 wind vectors or magnetic field vectors, whatever you like. We support contours, which are just showing a 2-dimensional contour on an arbitrarily oriented plane. So you can take a plane in 3D, orient it however you want, and draw contours on that. Or you can draw contours on 2-dimensional variables, usually at the surface. The flow renderer is something I'm not going to get into today if I don't have enough time. But it's one of our flagship renderers. It allows you to do what we call path lines and streamlines. So that's not the right video. Here we go. So these are streamlines of the Marshall Fire that we use Python. We were trying to find the atmospheric rotor that was theorized to have happened in the Marshall Fire. We think that's it right there. So these are streamlines. They're time invariant at a single time step. And this is a column of streamlines that we're just traversing up and down the y-axis to show what the wind is doing at a single time step, time invariant. The other kind of flow that we support is called path lines. And let's see. And this is basically just taking a bunch of feathers and throwing them into a tornado, like if you ever saw the movie Twister and they open up Dorothy and all the robots fly into the thing. You can basically effectively do the same thing in your simulation by throwing in this type of flow that we call path lines. But I'll get into that. It's a complicated renderer, but I'll get into it if we have time. We also support base maps and images to give context on where we are in a simulation. ISO surfaces are like a contour, but in 3 dimensions. Every point along a surface will have the same data value that you select. We support model rendering, so with STL files and things like windmills, you can throw those in alongside the turbulence in your simulation. Particle renderer is disabled right now because I don't have any particle data in my data set, but like I said earlier, we can put that Lagrangian point data alongside an Eulerian simulation if needed. Slices are just arbitrarily oriented planes that show a single variable. 2D data is just a color map showing a 2D variable. Volume is, I'll get into more about how volume rendering works when I actually do it, but it's basically, if you have something like a cloud or smoke, this applies opacity and transparency to the entire 3D field of your variable. And then finally, there's a wireframe renderer just showing the grid that your data is on. I'm going to start with the image renderer to get a base map and get some context of where we are. Again, this is the East Troublesome wildfire in Granby, Colorado. 3rd largest wildfire in Colorado history, I think. But anyways, I've instantiated my renderer. I have my image. I click on this eyeball to turn it on. And right now we have a very, very coarse map. So Vapor comes bundled with these maps. If we made them any more resolved, Vapor's distributable binary size would get huge. And so we have to limit ourselves on what we ship with Vapor. My favorite tool for getting georeferenced imagery is a NASA tool called Worldview, where they offer free satellite data. And so what you can do is just go to worldview.earthdata.nasa.gov, and they give this interface of all these different satellite products. And I think, gosh, everything's covered in snow. I'm not sure. I think Boulder's somewhere around here. So Vapor requires a geotiff image if you're going to do something like this. To do it with Worldview, you can click on this camera icon, select the area. Make sure to select geotiff, not JPEG. Geotiff just contains georeferenced spatial information that Vapor can read, and then you can download it. Now, this is not going to be a very good image because it's all covered in snow, but this is like real time. You can change the date, and so it might take a little hunting through time and space to find the right image for your rendering. But now that should have been downloaded, that's a nice Vapor. I can go to, I should speak to these tabs. So Every renderer in Vapor will have a variables tab, an appearance tab, and a geometry tab. And these correspond to what you're rendering, how you're rendering it, and where you're rendering it. So once you kind of understand how one renderer works, it's the same thing for the others. For the image, I'm going to go to the appearance tab and select my newly downloaded image. There it is. Now I go to my variables tab and I can select what I'm rendering it with, what variables are being applied, pick my height variable. And here we can have see the mountainous terrain. Again, I think the mountains just got dumped on, so it's not a good image, but that just demonstrates how you can acquire imagery. I have another one that I got previously that's also in the example folder. So I'm going to select, yes, snapshot. And here we have Lake Granby and Grand Lake, roughly during the time of the wildfire. So let's get some actual variable data into it now. So to do that, we have a context of where we are in space with our map. I'm going to create my next renderer, which is going to be 2D data. And with this, I'm going to show the fire perimeter at this current time step. So immediately, I've instantiated it. I'm going to turn it on by clicking the eyeball. And we have this 2D plane in the middle of our domain. The next thing I'm going to do is go to my variables tab. Again, this is what we're rendering, what variables are being applied. The color match variable is fire area, and I'm going to apply height to it. When I do that, I get this phenomenon. This is called, in OpenGL parlance, this is called Z fighting. What we're doing is we're drawing two planes at the exact same location in space, and the graphics card doesn't know what to show where, so the two planes fight each other. In order to fix this, I'm going to go to my geometry tab. Again, this is where we're rendering, and every renderer has a transform table, kind of like what we did with the data set. If I click on the data set, we scaled that by 5, and every renderer in the data set will be transformed by these parameters. My renderer can also be individually scaled and translated and et cetera, according to each axis in the same way. So I'm going to scale, or translate my 2D renderer by 50 meters, and now it's placed on top of my map. Map's on the bottom, 2D renderer is on top. And we can't see the map anymore. So what we need to do now is apply color and opacity parameters so we get a better, more compelling visualization. So again, variables is what we're rendering, appearance is how, and geometry is where. I mean, the appearance tab of this 2D renderer, we have this object called the transfer function. And this is kind of the beating heart of Vapor. And this is not the best transfer function to start off demonstrating. I'm going to change my variable to height. So now we're looking at the height variable with a height variable applied to it. And our transfer function looks like this. It's just a probability distribution function of our variable with values spanning from roughly 2,000 to roughly 4,000 on the right. Values on the right are having red applied, going through this color map all the way to blue to the low values on the left. I can take these color control points and drag them to the right and change how the color is being applied to the different values of the variable. I can do the same thing on the, on the right side with these color control points. And I can double click at any point on the color map and create a new control point and adjust things by hand this way, and double click again to delete. Okay, so that's how color is being applied to these values of my variable. Opacity is controlled with this black line up here at the top. So if I take these control points and drag them down, I'm now applying transparency or removing opacity based on how high up these are on the y-axis. I can drag them all down, and all of my data values, except for these ones at the far right, disappear. And also by dragging them all up, everything is completely opaque. So that's the basics of how this transfer function works. I'm going to go back to my variables tab and do my fire area variable again. Go to my appearance. And again, this is a bad example because the data values are just an impulse on the left and an impulse on the right, and very few data points in between where the fire is actively burning. What I'm going to do is mask out the unburnt areas. And so now we have the fire perimeter superimposed upon our map. But I'm still not really satisfied with this color map we're using. Vapor comes with a whole bunch of other ones that are more suitable. So I'll click on this gear icon and go down to load built-in color map. We support divergent color maps, which is what we started with, two colors on the left and right, meeting at white in the middle. Highlighting are kind of weird, we'll get into those. And then sequential. For the fire perimeter, I always use this one called black body up here at the top. So when I click on that, we have our built-in color map loaded. But the problem here is that the burned area is white and the unburned area is now black. If I turn the opacity back up, everything is blacked out. So we want the opposite, where the burned area is dark instead. So I can right-click on the color bar and reverse the color map. And then finally, I want to add some transparency to the black area so we can kind of see through into the terrain where the fire is already burned. So that is the basics of the 2D data renderer. I'm going to stop there and come back to Vapor after we do a little bit of Python. So to do that, let's see. I'll minimize Vapor, minimize Chrome. And let's see, I'm going to go ahead. I might as well start from here. So to go through some of the basics, this zoom. Okay. So I'm just going to start marching through this documentation, and then towards the end we'll get into some more of the interesting stuff. But this starts off with just showing that everything that is in Vapor is exposed through Python. So the first thing I'm going to do is define a home directory, and if you copy the data from the Google Drive, you'll have to set this home directory to wherever you downloaded the content. And the first thing I'm going to do is import the session module so that I can create a session and start manipulating it. After that, one of the biggest things you're going to need to know is how to find help. So you can call help on different objects like so. Help on session.session will give you the class methodology and all the functions that come along with it. You can also look at our website. I can find Chrome. Let's see, I'll do our Python documentation, Python API reference. You can find all the classes and all of the functions here as well. But it's all there whether you go about it through the website or through the actual API itself. The next thing I'll do is load data. So I'm using this path library, path and blotting a little bit easier. And I'm just loading in all the files in my home directory, in the data directory that I defined before. So those are all the files. I'm going to show some metadata about the data, about our coordinate variables, actual variables. And finally, we're going to start making a 2D render and actually get stuff to show up in our Jupyter notebook. So that looks nice things. So from Vapor, I import the renderer module. I create a new renderer defined as a 2D data renderer like so. And then I set the variable name to fire area like what we did in Vapor, just programmatically. And then to show it, we call show upon the session object. We can apply height variables in a similar way, just programmatically. And it doesn't look that much different. You can see kind of the border, but we're looking down the negative z-axis, and so you don't see much of a difference right now. I can't manipulate this box yet, so the next thing we're going to do is create an interactive visualizer. So that's using this module called Jupyter Vapor Widget, and then we just instantiate a Vapor Visualizer widget based on our session. We render it, and then we call the visualizer. And then at this point, we can control the visualizer in the same way that we did in Vapor. This can give you a way to demonstrate 3D visualizations in a simpler way than having to pull up the entirety of Vapor and all these parameters alongside of it. You can create a visualizer showing a simple visualization of just what you want to show without the plethora of other options that come bundled in the desktop application. I'm just going to show real quick how you can interrogate things like the transfer functions. In utilities, you can show histograms using matplotlib. If you pass in a session and the current renderer, you get this histogram like we saw earlier. You have two impulses, one on the left, one on the right for the fire area. You can take that transfer function and then apply opacity to it. So you can get the histogram, set some opacities. So at the data value of 0.2, I will have an opacity of 0, according to this. And at the data value of 0.8, an opacity of 1. And then we just pass in those opacities to the plot and then show it. And here we have something similar to what we saw with our transfer function over here. Let's see, render the current session in an interactive visualizer. So we didn't apply it. We're going to, all right, so we set the opacity control points to the opacities that we defined, and then we just re-render that visualizer, and now we can manipulate it in the same way that we did before. We can also load in built-in transfer functions like what we did with the gear icon in the desktop application. And here we're just loading in sequential black body, not doing any reversals, not doing any opacities, just showing that you can load these transfer functions in the same way as you can do with desktop. And then you can load transfer functions that were configured in Vapor. So I guess I glimpsed over this. In the desktop application, with this icon, you can save your transfer functions for later use. And so you just give it a name, use troublesome.tf3 would work. TF3 is the extension for transfer functions. Fire area, I believe, is the one we're using for the 2D renderer. And here we have a similar transfer function to what we saw earlier. A little hard to see because we have no map underneath it. But the transparent darkened center is being shown along with the red fire perimeter, according to this fire area.tf3 transfer function. Last thing I want to show in this chunk of Python is interactive sliders. So I was mentioning earlier, if there's only one thing you want to show in your visualization, you can very simply show that with a Jupyter notebook by configuring your session in the desktop. And then if you want to add a slider that adjusts just one parameter, it's kind of like a foolproof way to show an example without having all these different other widgets coming up. So that is a different Jupyter notebook that I'm going to come to over here and restart the kernel, clear the outputs. And let's see. Yeah, this example is not in that directory, but after you install Vapor, let's see, using Conda, you can do, okay, so here I have Conda activate 2.9.1. There's more examples you can find, as well as on our website in Conda prefix, lib, Python, 9, site packages, Vapor. And here you can find sample notebooks, and what we're going to look at from the examples that come packaged with Vapor's Python package is called visualizer widget example right here. And so I'll open up my Safari window. And the reason I'm using this example is because certain renderers are more computationally expensive and, than others. So with Vapor comes these example utilities where you can open very simple example data sets and they're more responsive. So I'm going to that for this. And simply going to create an ISO surface. So create a new renderer on our data set called a volume ISO renderer. We set the variable name just to the first, well, it says 2D variable, it should be 3D. But anyways, we get the ISO values. There should be 1 by default, and we're just going to add 0.1 to it. In the session, we're going to do show it. So there's our first ISO surface. And then we're going to create a visualizer like what we did before, so we can actually rotate the scene. So that's using the Vapor Visualizer widget, the session applied to it. Now we can move around and see our ISO surface from different angles. The last thing we're going to do is create an interactive ISO value slider using IPy widgets. So we're going to first acquire a transfer function using the renderer's getPrimaryTransfer function and acquire the data range for that. We're going to apply this data range to the slider. We're going to find a callback so that when this slider gets modified, this callback applies the change that has happened. And then we will instantiate the slider as a float slider, give it values of a current value, a minimum and maximum value, and a step size. And then once we do that, we apply the callback that we defined to the slider itself. And then we create a kind of an organizational set of a structure to what we're going to show. We create a vertical box that contains two things: the visualizer that we have up here, as well as a horizontal box. And that horizontal box includes a label and the slider itself. And so once we do all that, we get something like this. Our vertical box contains everything, including the visualizer, the slider label combination below it. And then the horizontal box here, of course, contains the label and then the slider, and then we can change this. And that's a bug. That second isocircle shouldn't be there. I do that. But yeah, we'll have to look into that. But one way or the other, this shows you how you can manipulate one parameter in your data set in a simple Jupyter notebook without all the cruft that you might not care about in Vapor as an application. But again, you're probably going to start off with using Vapor first, and then save a session, and then apply a slider like this, and then share the Jupyter notebook. At least that's my typical workflow.
Have you looked at PyVista at all, which is built on VTK, but it accepts like X-ray data sets as input?
I haven't heard of it. We also can read X-ray data sets as well. So maybe there's some redundancy that we didn't know about with that.
Yeah, I think because it's not, you mentioned it's built on VTK, but it's worth, yeah, I would just search PyVista or whatever. And it's not one for one. They don't have a desktop GUI app, but definitely it was meant to be like a geo add-on to VTK to make it easier to read in like 3D gridded data sets.
That's one of the things that I need to work into this tutorial is reading X-ray. I'm short for time.
Yeah, no, for sure. No, I'm not. Yeah, no, this is great. I'm learning a ton more like what's out there, but I would say like, especially if you're going to show off the Python hooks, if you're going to deal with 3D gridded data in Python, you're going to use X-ray. So.
Cool, we'll get to it.
Yeah, no, this is great. Sorry, I wasn't trying to.
Oh, no. If you guys have any questions, like, please, shout out. It's
yeah.
Good to get the feedback. But I think that does it for the basic example of our Jupyter widget. Next thing I want to do is jump back to Vapor to do our DVR and show you our Python engine, because we have a Python API. You can control Vapor with Python in the API, but you can also manipulate variables within Python to do things like derive things like wind speed. So I think the next thing I want to do is jump into the DVR and then maybe go to wind bars and wind speed. So to create my DVR, press the plus icon, double click my volume, and I'll just turn it on and make a quick statement on what the volume renderer is. So the volume renderer is using a technique called ray casting, where we're basically like firing a laser through every pixel on the screen that's going through the grid and sampling the grid until we reach a value of maximum opacity. At that point, we stop sampling and we return an opacity value, and you have your cloud or your smoke or whatever you're after. You can see right now, this rendering is very fast for the volume renderer because everything is at maximum opacity in my transfer function. These lasers we're firing through the screen are hitting the first data value of the grid and they're stopping. Once we apply transparency, it's going to get a little bit slower. So this kind of brings up the notion of what are the data formats that we created called the VDC, which is, it takes your data, if I go to the file menu, I can open VDC. And basically you can take these data formats, convert them into Vapor's data collection format. And what will happen is Vapor will apply a wavelet transform on the data that allows you to look at your data at different levels of refinement. So if your data is massive and your volume renderer is taking minutes and minutes to produce an image, you can convert to VDC, look at things at low fidelity, kind of get the observables that you're sort of going after, and then once you're satisfied, crank up the fidelity to the maximum to perfect reconstruction within floating point error, and then press play and capture your full sequence. So that's a usability thing that is useful for the VDC with large data sets. But back to the volume renderer, it's the same thing as the other guys. It's variables is what you're rendering, and so for this, fire smoke is the one I'm after. So I pick that. Appearance is how we're rendering it. And so here's our transfer function. I think for the sake of time, I can load a transfer function that I prepared ahead of time. And it's, of course, smoke.tf3. TF3 again being the file extension for the renderer. So once I do that, I have my pre-configured transfer function hiding most of the values at 0 because, this is a big debate in the wildfire community. Where does smoke begin and where does it end? And so it's arbitrary, and that's kind of what we're seeing here, just going for an aesthetic, I suppose. But here we are, just slowly ramping up in intensity as we get over to our more high smoke values. And so I have my volume renderer. It's interesting, MacBooks have a timeout on their graphics cards that we've been hitting. That's why I couldn't plug into HDMI. We hit the timeout if I have 2 monitors with this data set and the application crashes, but Zoom shouldn't introduce that issue. What I'm going to do is touch on the Python engine real quick, and then we'll go into keyframing. So, is this the right order? I don't think so. I'm going to turn off my volume renderer real quick and do a barb renderer because I'm going to derive wind speed using the variables that are in the data set. So press the plus button, double click barb, and then go to my variables tab. I'm going to do surface barbs. So by default, we're looking at the 3D variables. I'm going to pick 2D. Oh wait, this data set doesn't have the 2D wind field. All right, I'm stuck with 3D wind fields. That's all right though. I'll just go ahead and turn it on by default, according to the default parameters. There are my wind barbs. I can go to my appearance tab and then zoom is in my way. There we go. So all of the color mapping is and the transfer function are done the same way, but the parameters that are unique to barbs are here at the bottom of the appearance tab. I can max these out on the X and Y axes, and we just have tons of barbs like that. Adjust the length, make them thinner or thicker, whatever you need. If I was rendering 2D barbs, I would be able to apply a height variable in the same way that we did with the 2D data and the image. But since U10 and W10 aren't here, I can't do that right now. But what I'm going to do is make these a little more prominent. And then what I'm going to do next is create a new variable for wind speed and then apply that to the barbs using the Python engine. So I go to the tools menu, go to Python variables, and create a new script. I'll call it speed. My input variables will be U, V, and W. My output variable will be the unstaggered grid. Let me see if I can remember if I can get this right. Speed, ED. So what Vapor needs to do is first unstagger these grids. They're at different grid points. So Vapor comes with a utilities set of functions. So from Vapor utils, import everything, and then, gosh, U unstaggered, I'm going to call staggered to unstaggered grid. We're going to feed it U, and I think the axis is reverse C order. So U, and then the axis is X. V unstaggered will be the same kind of thing. And then W unstaggered, same kind of thing. Got a V, got a 1, got a 0, and U got a W. And then finally, I can say that speed is equal to mag of UU, VU, WU. Let's see if this works. Locked out. All right. Save that to session, and now I have a variable in my data set called speed, which is derived off of my input variables. So I go to my variables tab for what? Color map variable, I'll pick speed. I can go to my appearance tab and pick a better color map. Sequential, and that. And then play with my transfer function in the same way that I did before. So that's the Python engine and the barb renderer. I'll turn that off for now, turn on my volume, and then move on to some of the cooler parts of Python. So I have my volume. What I'm going to do next is what I mentioned earlier, keyframing, where we're going to kind of cinematically move between 2 perspectives. I'm going to pick that perspective right there. I'm going to save my session. Call it P1, perspective 1. And then come over here to the east side. I'll save this session as P2. Save it. Okay. Time series animation. I guess I skipped this cell. I don't run it. I think this is just going to show an animation of our frames, and that might take a minute to run in the background. In the meantime, I'm going to move on to the keyframing portion and then come back up to the time series animation because it's going to load every time step and render it. So that'll take a second. So we're going to load our session and camera modules. Session 1 is an instance of session.session. And let's see. I think I called this P1.vs3. So we're loading P1, our initial perspective. And then what we're going to do is acquire our camera. And the camera is comprised of 3 different components. There is the direction the camera is looking, there's the position that it's in space, and then there's the up direction. And these 3 triplets define how the camera is oriented and what it's looking at in space. So we defined our direction triplet, our position triplet, and our up triplet on X, Y, and Z for our initial position, loaded from P1.vs3. We're going to do the same thing for P2.vs3. So now we have 2 pairs of direction, position, and up vectors. We're just going to now take the difference between position 2 and position 1 for each component. And then over 50 steps, we're just going to do a linear interpolation between those 3 components. And then finally render whatever the camera is looking at as we interpolate through 50 steps. And let's see, I put that in my home here under captures. Let's see if this is refreshing. Yep, so it looks like, see, 247 is marching down the list. And I'm also demonstrating that you can just save JPEGs, TIFFs, and rasters. Using this technique, you can also create animations like what we skipped over up here when we went through the time series. We loaded this session file, and then we got the time steps. And for each time step, we saved it and showed an interactive animation, and then you can show it interactively too, as opposed to saving actual files. But the keyframing sequence should be done. Yep. I'll just select all my files and open them. And as I iterate through them, we should be able to see our camera interpolating between the 2 positions. So that's a way to specify 2 different points to interpolate through. For the next example, we're going to do that z-axis orbit. Camera orbit, and we're using SciPy for this and some linear algebra functions that I won't get too deep into. And I will admit, something that I think we should do in the future is implement this orbit utility and the keyframing utility as a simple function where you're just feeding it in a few parameters instead of having to go through all the math. I think that's coming in the future, but for now, all of the code that does this is available on our website and in the Google Drive. So you can copy this and achieve the same thing, just with a lot more verbosity. And yeah, I'm not going to go through quite all of it. But yeah, you can see down here it's rendering. And this will be rendered as an animation, similar to what we did up top, not as a series of images. So I think I mentioned at the start, I was asked to shorten this to 45 minutes, like overtime right now. We were going to do a I guess like a, what do they call it? Office hours kind of thing, open work session. So once this is completed, I think we can transition over to that unless you guys want to see the flow rendering. I can just show you on your own data as well. I can also take any questions in the chat by any chance.
I have not seen any questions online, but if there are questions online, feel free to put them in the chat and I can read them out to you.
Okay. Okay, so we just rendered that. And I'm sorry, we rendered this to an actual MPEG using FFmpeg. So let's see. There we go. So this is just rotating around the scene along the z-axis. And that's all I got.
This is really nice.
Thanks. So yeah, I'll just chill out here, I guess, and I'll be available if you guys have your own data that you'd like to look at or anything else.
And then can you use Vapor with non? geographic data? Like you just have like 1, 2, 3, or like just indexed for X and Y?
I I think that falls in the category of the brick of values,
Okay,
and that has to be on a regular grid.
yeah,
So if you just have like a bunch of floats or integers or doubles, the brick of values is gonna be your best bet. There's also the VDC tool that I mentioned earlier that can read raw data,
okay.
but unless it's huge, I probably would start with the brick of values first.
Could you ingest like just a X-ray data set? Using Python that isn't a CF X-ray data set?
Not into the desktop as it stands,
Okay, but what about using it and
the API.
yeah, could you ingest data just using the Python API, or do you need to use the desktop app?
You can manipulate it with the Python API, but Vapor would not. It's a good question. I don't think that would work because, I'm imagining you could load in the data through X-ray, save a session, see if Vapor could read that. I don't think the data readers are gonna like that.
Okay.
That's Python specific, but it's an interesting thought.
Yeah, I'm just thinking data that's in netcdf format, like biology data, thin section data, things that are small that are gonna be just like indexed. You know, like 300 pixels in X and 200 pixels in Y, which you would read in using X-ray, but it's not like a geographic coordinate, if that makes sense.
Yeah, you can do that if you make it CF compliant. There's just like some attributes on the coordinate variables,
Okay,
like the axis coordinate variable, units, and time, if there is time. But
Yeah.
you can make that stuff up too.
okay. Yeah, I'm sure you can, there's like a way to finagle that.
Yeah, if you have a sample, I can like take a look at it.
Okay,
Is the current CSM output CF compliant?
CESM. I'm not familiar with their data output. Is it? John, do you know?
It's compliant enough. I think you can read CAM files directly in.
Oh,
How do you create your own color table? Because you said, for fire, you create your own. I guess you experiment with various tables. How do you save them? Probably that's.
Right, so let's see. If I was to recreate my smoke table, let's see, I go to my transfer function. And the first thing I would do, I would start with some of the built-in color maps as a starting point. So go with black body. And then I think would reverse it. And I'm cheating right now because that's almost what we had before. But let's say I wanted this control point to be a little darker. The color selector is right down here. So you can add new color control points by double clicking. And then you can click the color selector, and then if you want to, do whatever you like, you can pick green. And then we'll do an interpolation based on there's different interpolation methods that we use for our color maps. Let's see, color interpolation. Yeah, we're using a divergent color map here. That's probably more appropriate. Maybe linear would be, but who's going to add green into a smoke field anyways? But that's kind of how you go about it. Does that make sense? Like,
Yeah, after this, how do you save that? If you find one that really like.
yeah, so
Oh, I see.
they're all saved to your session as well.
Okay.
So when you save the overarching session with all your parameters, it's going to be included the next time you load Vapor, but also you can apply the transfer functions to different sessions right here. And that will give you a file called TF3. It's the transfer function.
Great. Thanks.
And this was a really interesting simulation that was done over at RAL earlier this year. What happened with during the East Troublesome Fire was it was a month and a half long, and it was over 200,000 acres, but about 100,000 of those acres burned in a single 24-hour period. And firefighters and boots on the ground were going crazy. They didn't know what to do because the forecast didn't see this 100 1,000-acre explosion coming at all in the forecasts. So what ended up happening was that they realized that the fuel sources were wrong. The beetle kill up in the mountains combined with windstorms that knocked the trees down caused the fuel inputs to be wildly off. And the United States Forest Service can only survey these trees every 5 years. So what RAL did was they implemented this satellite random tree or random forest algorithm to take, I think, actually the same data from the Worldview website, from Sentinel-1 and Sentinel-2, to be able to categorize the fuel sources in real time. And so once they could do it in real time, they had, I think, like a 48% increase in the burn area accuracy, which, before they had that appropriate fuel source, it was just wildly underestimated. And again, this data is available on the Google Drive if you guys would like to take a look at it yourself.